Okay, so today we're going to be talking about prime and composite, and then also greatest common factor and least common multiple. So the first thing we're going to start with is just find natural number factors of each number. So we just want to find all the possible factors that can multiply together to give us 12. So on our first example, the easy one is 1 times itself, right? So 1 times 12 is 12. Give me something else. 2 times 6, good. So 2 times 6 is 12. Anything else? Yes, 3 times 4. So all of these are factors of 12. Now we could put that in order if we wanted to, but order doesn't necessarily matter when you listen to factors. So the next one we want to look at is 28. All the factors of 28. So it's easy. Let's just start with our 1 times 28. What else comes to mind? 2 times 14, because it's an even number. We know it's always divisible by 2, so that's easy. 2 times 14, and possibly one more. What is it? 4 times 7. Good. So one of the first set of questions you'll be asked is to name all the natural number factors of each number. So that's pretty easy. So just go through and label all the factors. And then another thing you'll be asked to do is to use the divisibility test for each number. So on that sheet, when we talked about all the divisibility rules, we want to use those for these. So when we start with the number 321, actually I'm just going to take a minute and write out all my ones that we looked at. So we looked at 2, 3, 4, 5, 6, 7. Okay, so we have the divisibility rules for basically these numbers right here. We're going to go through each one, and we're either going to circle it or we're going to mark an X on it, just so we know that we've gone through each divisibility rule. So for 321, is it divisible by 2? No. So mark it out. What about 3? Yes, because it says the sum of the numbers, so let's add them up. 3 plus 2 is 5, plus 1 is 6. So when I add all the numbers up, the digits, I get 6. And then my question is 6 divisible by 3? And since we say yes, we say 321 is divisible by 3. Okay? 4. 4 says the last two digits. The last two digits are divisible. So what's 21? Is 21 divided by 4? No, so it's not. 5, does it end in a 5 or a 0? No. To be divisible by 6, it has to be divisible by 2 and 3. So did we previously circle both 2 and 3? Nope, so the work's already done there, so not 6. I skipped out. I added 7. 7 was the one that we did. So we'll go to 8. 8 says the last 3 numbers is divisible by 8. So 321, that does not divide by 8 evenly. 9, for the divisibility rule for 9, the sum of all the digits, so we add them up again, 3 plus 2 plus 1 is 6. Does 6 divide by 9? No, so not 9. 10 must end in a 0, not 10. And for 12, we have to have divisible by 3 and by 4. So did we circle 3 and 4? No. So the only thing that 321 is divisible by is 3. The only number. All right. So we have our next number. I'm going to take a minute to jot down. So I have 2, 3, 4. Alright, so remember the handout that I gave you included 7, but the textbook for this one doesn't. And we just said if we ended up asking about 7, we just divide it out and see if it had a remainder of 0 or not. Alright, so now we have a much larger number, 36,360. We want to go through all the divisibility rules. So first of all, is it divisible by 2? Yes, is it an even number? So it ends in a, yeah, so even number. For 3, we need to add those up. 3 plus 6 plus 3 plus 6. What's that add to? 18. And does 18 divide by 3? Yes, so divisible by 3. Good. For the divisibility rules for 4, you look at the last 2 digits, which is 60, and see if that divides by 4. And it does. 15. Yeah. Yes, because 15 times 4, so 15 and 15 is 30. 15 and 15 is 30. 30, 30, 60, yeah. So 15 divides by 4. For the 5's rule, does it end in a 5 or a 0? Yes. For the 6 rule, it has to be divisible by 2 and 3. Did we circle both of those? Yep. So in this other one, does it divide by 8? You look at the last 3 numbers, 360. 360 does divide by 8. Okay. Then you have 9s. The 9 rule says add them up again, which we got 18, I believe, the last time we added them. Does 18 divide by 9? Yes, good. For 10, does it end in a 0? Yes. And for the 12 rule, is it a factors? Does it have divisibility by 3 and by 4? Yes. So we circle 3 and 4, so we can circle 12. So this number is divisible by all of those. So prime factorization, now we're just going to do a factor tree, and this is something that you've done before. So 168 is an even number, so I'm usually just going to start with 2, and 2 times what gives you 168? You can divide right there, and that's going to be 84, right? Yeah. Now, whoops. 2 times 84. 2 I'm going to circle because it's prime and it can't go any further. 84 is an even number, so I can take at least a what out of it? Another 2. So 84 is 2 times, now divide 84 by 2 out to the side, so it's 42. Every time you get a prime number, circle it because that's a dead end part of the tree. So the next 42, it's even, so at least a 2 can come out of it. So it's 2 times 21. And 21 is not even, but it is divisible by 3, so what is that? 3 times 7. Well, 3 is prime, so I circle it, and 7 is prime, so I circle it. Now that my tree has all prime numbers, I can write the factorization out. So one of the ways you could just say 2 times 2 times 2 times 3 times 7, or the other way that that is expressed is 2 to the what power? Good. Times 3 times 7. Either one of those. Now, there is some variance you can have here. Like, for example, and there's no, the way I get there isn't any better than the way you get there. Because some people right here, let me come to the side, they could have said what times what? 6 times 7 and said 7's prime and 6 is 2 times 3, and it doesn't matter because it still got 2, 3, 7, just like this person got 2, 3, 7. So how you choose to break down your tree isn't necessarily most important as it is that you just get everything to be a factor of prime. So basically, when you branch off and you do multiples, you keep going until you get a prime number and circle it. Our paths might be a little bit different, but if we both do the math correctly, we should get the same prime factorization. Okay, so 468, I'm just going to divide it because it's a bigger even number. Divide it by 2 and try to get it a little bit lower. So divide by 2. Each component divide by 2 and I get 234. That's even as well. So I'm going to divide a 2 out of it. And that's going to give me 117. Now, 117 is a number I'm not very familiar with, so I need to kind of think through my divisibility rules to help me out a little bit. So after 2, what's the next one on the list? 3, and for the 3's, I add them all up. So 7 plus 1 plus 1 is 9. 9 divides by 3, so I know this is divisible by 3. These are my divisibility rules. So 3, and then I just need to go off to the side and divide that out. So 39. Okay, 39 is also divisible by 3 because 3 plus 9 is 12, and 12 divides by 3, so I'll take another 3 out of this, and that's just going to be 13. 13 is prime. When you get the prime number circle, I'm added that in, so now I'm going to come back and say 2 squared times 3 squared times 13. Okay, so the next one is, it gives us 2 divisibility rules that the textbook didn't necessarily breach. So the 7s, which I gave you one with a handout that included it, but it was extra, so we didn't really look at it. And then 11 wasn't on our list because they aren't like quick hit, real easy things. So what's your tactic for this? Just take those numbers off to the side and divide them and see if you get a remainder of 0 or not. So nothing tricky there. You're just going to have to go out to the side and divide those. So do those 2 on your own. See if you could work those. So the first one I got yes, because I got 30,608 times 7, and I had no remainder. And we're going to look at the next one. So you can see that there's going to be a decimal that keeps going, so we know that this one is not. All right, and on the next two, you'll take the time, you do the same thing. Basically, you're going to divide those out. So you can do that and practice them later. The first one is no, and the next one you should get yes. So, like I said, there's not anything new in this lesson that's a skill for that. We don't technically have a divisibility rule that we like to use for 7s and 11s. If you're just asked to do a question of those, divide those out. If it divides into a whole number with no remainder, you know it's a factor or it's divisible. If it does not, you get decimal places, you know it's not. So check you can do the same thing for 11. The first one should come out no, and the next one should come out yes. Our next question says, determine all the possible digit replacements for x so that the first number is divisible by the second number. Okay, so we're looking at this particular number. When it's saying we want to know if that number, which we're going to have different values there, is going to be divisible by 2. So first off, what's the first one we want to test? Actually, I'm going to not put a check there, but what's the first one we want to test? When x is 0. So let's put a 0 in there. And we want to know if it's divisible by 2. Is that number divisible by 2?
Yes.
Yes. Okay. So let me do this. I'll highlight it because it works. All right. The next one we want to test is if I put x is 2, so I plug in a 2 right here. I want to know, is it divisible by 2? So that's how we're looking at this. Is it divisible by 2? Yes. So I'm going to highlight it. Now I'm just going to keep moving down. If x is 4, that means there's going to be a 4 there. Is that number now divisible by 2? Yes. Okay, if I put a 6 there, remember the 6 digit says if it's divisible, it's is it divisible by 6? So 2 and 3, right? Okay, so what do you think there? Yes. And what about by 8? Let's put 8. We put an 8 there. Let's see. Yes. So it's divisible by 2. I almost confused myself for a minute because I almost made it harder because then I started looking at that. I was like, divisibility rule for 8. It just wants to know, plug those values of x in, and then once you do, ask yourself, is that number divisible by 2? Which, as long as it ends in an even number, they're all divisible by 2. So you'll have a question that might look like that. So it asks you to insert different values in x and then determine divisibility for said rule. So for this case, it's divisible by 2. All right, so that was the first time of just working on factors, prompt factorization. Now we're going to move to greatest common factor and least common multiple. I'll do 2 different methods for it, although, I mean, the first time I'll use the factor tree method, and the second time I'm going to use a different table method that I'll probably use more consistent. If you prefer one way over the other, at the end of the day, if you're doing it correctly, I'm okay with that. I'm just going to kind of show you both so you can feel out like what works for you, and we'll go from there. So the first thing you want to do when you're asking for the greatest common factor, you want the the largest thing that they have in common, we're just going to break 60 down and break 140 down. So we're going to start here, just do scratch work. So factor tree for 60, well that's 2 times 30. 30 is even, so 2 times 15. 15 is divisible by 3, so 3 times 5. Okay, so for 60, I have 2 squared times 3 times 5. Over here, I'll do the same thing with 140. And the more that you do these, the faster you'll get. So 70 is 2 times 35. And that one's just going to be 5 times 7. 5 is prime and 7 is prime, so it's 2 squared times 5 times 7. Alright, so what are the things that they have in common? The greatest things that they have in common, and what else? Good. So when I say my GCF is going to be 2 squared times 5, which is 2 squared is 4. 4 times 5 is 20. Okay, that's one way. That's using the factor tree. The next one's large numbers, and that's okay. I'm not saying that necessarily one method is better than the other, but I will start using this method probably more. If I take both of them and I put them in a table like this, I can kind of work with 2 at a time. So both of them are even numbers. What will I divide by first? A 2, right? So then when I'm dividing, 540 divided by 2 is 270. 1200 divided by 2 is 600. When I look at those numbers again, both of them end in 0, so I'm going to take another 2 out of them. Divide by 2. 270 divided by 2 is 135, and then this is 300. Well, 1 ends in a 5, so my 2's are over. My next divisibility rule is a 3, or I could have jumped to 5, but we're going to see 300 is easy, because 3 divided by 3 is 0, and then 5 plus 3 is 8, plus 1 is 9, so 135 adds to give us 9, and that's divisible by 3, so I'm going to divide a 3 out of both of them. Um, 45 divides by 3, but 100 doesn't divide by 3, so I'm going to look at the next problem number, which is 5, and this is easy because they both end in a 5 or a 0. So 45 divided by 5 is 15. Oh, I mean not 15. 3. 9. 9 times 5 is 45. We're struggling writing and talking at the same time this morning. So what's 100 divided by 5? 20. Okay. Now 9 and 20 don't have anything in common. So there's nothing else I can divide there. So your GCF in this one comes from, these are all the factors that they had in common, right? All the factors that was divided out of them, both of them. So the GCF here is just going to be 2 squared times 3 times 5, which in this case, 2 squared is 4, times 3 is 12, times 5 is 60. So our GCF is 60. Okay, so that's 2 different methods for GCF. Now we're going to look at least common multiple. And we're going to do the same thing. We're going to do one with the tree and one with the table and go from there. Start with 54. Now I'm just going to do this a little bit different just so it doesn't make you uncomfortable if it happens. So I'm going to say 6 times 9 is 54. Instead of starting with, I could start it with 2, 3, 4, and did it in order, but I want you to see that it's okay if I just start with 2 things I'm familiar with and keep going. So 6 is not prom, so it needs to keep going. 6 is 2 and 3. Now both of those are prom, so that's done. I go back up to 9, and it is 3 times 3. So 2 times 3 to the 3rd power. And for 30, I'm just going to jump out and do 6 times 5. You could have said 5 times 6. You could have said 3 times 10. You have lots of options. It doesn't necessarily matter, but 5 is prom. 6 is 2 times 3. So 2 times 3 times 5. Okay. For the least common multiple, we're going to include at least one of everything, and you choose the largest multiple of it. Okay, so for example, we'll have 2. Then we're going to have, out of the 3's, this is the larger one, 3 to the 3rd power. And this one doesn't have a 5, but this one has a 5. So we have to use all of those. So you're going to have 2 times 3 to the 3rd times 5, which 3 to the 3rd is 27, and then 27 times 5 times 2 is 270. So that's the smallest, the least common multiple that they have in common. So if you were to take, another thing that you've done this before is if you took 54, you did all the multiples of 54. So 54 plus the next one, which is 54 plus 54. So 30, let's talk about 30 because it's easier. If I listed all the multiples of 30, it would be 30, 60, 90, 120. Well, if you did the same thing with 54, we have to keep going until we find the smallest one that they have in common. So when you factor it out like this, you're going to use one of everything. So if there's a 2, you're going to use a 2. If there's a 5, you're going to use a 5. And then if there's a multiple of 1, so one of this side was 3 to the 3rd, and the other one was 3 to the 1st, you use the larger of it, okay, for least common multiple. So here we're going to do 90 and 50, but we're going to use the table. So we'll have 90 and 50. Divide by 2. They're both ends and even. 45 and 25. Now, one question that you may have is, where with the table, with the tree diagram, I chose to do something that was real familiar, like 54. I did 6 times 9. I didn't stick to starting with the 2 as the lowest prom and then going to 3. But in this method over here, you want to start with your prom number, go from 2 to 3 to 5 to 7. So here, you do want to have some structure, because if I would have taken a 10 out of both of those, 10 would have been over here, but 10 is not prom. So I would have had to go do some more work. So the structure of this one is a little bit more strict in that you want to start with 2, then go to 3, then go to 5, like go through your proms in order. That's going to be better in this scenario. So now here, 3 doesn't work for 25, so then I go to 5, and 5 works. So 45 divided by 5 is 9. Actually did that this time, 9, and then 5, which I didn't necessarily have to. 9 and 5 don't have anything in common, so I stopped there. For least common multiples, we got to use one of everything. So you're going to use the 2, the 5, and you'll have 5 squared, so we have all of this. So it's going to be least common multiple, 2 times 5 squared times 9, which is 450. remember, just recall in least common multiples, the reason why you use all of them or least is because if you were to do this a way you've probably done it before, you could set up 90 and do all the multiples of 90. 90 times 2, 90 times 3, which is what? 270, 360, 450, and then here if you did 50s, you would do all the multiples 50, 100, 150, 200. And 450 is the least multiple that they both have in common. So that's the old school way of doing it. Now you have tree method when you look at the tree diagram method, how to assess that, or you have this table method, which the nice thing about this one is if I ask you the greatest common factor of 90 and 50, and I ask you the least common multiple of 90 and 50, you can answer those off this same table. But for this one, least common multiple is use everything. What if I ask you greatest common factor? Only use the left side, right? So what? 2 times off 10. So that's why I like to use this one. Not that you require or you have to. If you have a formula, which I told you we looked at it, to find the least common multiple, we'll look at this in a minute. You have that formula there, but let's go up to the side and work these two using our table. So if I have 32 and 56, let's just sketch it out and find this first, and then we'll go back and apply the formula to it and see if they line up. All right, let's divide a 2. So that's 16 and 28. Even again, so divide by 2, 8 and 14. Even again, divide by another 2, 4 and 7. Okay, that's as far as I can get, since if I asked you the greatest common factor, because I need the greatest common factor in my formula, what's the greatest common factor? 2 times 2 times 2. GCF is 2 times 2 times 2. Okay, so using my formula, least common multiple is equal to m times n. So 32 times 56 divide by the GCF of them, which we found to be 8. If you multiply that out and then divide by 8, you will get 224. Or using our other method, what could we do to get LCM? We can multiply all of these times all of these for LCM, right? So that would be using the old way, or using the other way and not the formula. LCM would be 2 times 2 times 2 times 4 times 7, which is still 224. So I don't really see a whole lot of fit for using the formula because, one, the formula makes me do that to get the GCF anyway, and if I've already done the work to do GCF, I'm just going to pull it from the table. But there is a formula, so it's good to know sometimes. There may be some situations if the GCF is really easy and you can read it off the top of your head to just do the LCM in this way. But for the most part, I tend to like the table method. The only thing is you have to be careful is you make sure on that one we'd like to go in order according to the primes, just so we don't get something that's not prime on the outside. But you have some leeway there, and then when you're working these, as long as you are doing it correctly, I'm okay with that. All right, so any questions?